In this video, we will discuss an application of definite integrals, which is calculating areas enclosed between curves. But let's start by kind of reminding us what the definite integral itself calculates. It calculates a net difference of enclosed areas. More specifically, if you have a function which is non-negative on an interval. So let's consider this function f of x on the interval from 0 to 2. Then the definite integral from a to b of the function, so 0 to 2 of our function, will calculate the enclosed area. It would tell us kind of how much area is enclosed underneath the curve. And let me remind you how we set this up. We said, well, maybe we don't want to necessarily calculate the area exactly, but what we can do is approximate it and then use that approximation to come up with the actual value. So we took this interval, in this case from 0 to 2, we broke it up into a bunch of subintervals. In general, you have xi minus 1 to x sub I, all the way over to xn minus 1, and 2 in this case would be x sub n, and then 0 would be the x sub 0. And then the idea is on each one of these subintervals, what we do is we draw a rectangle where I've used, in this case, the right-hand endpoint to determine the height. And we add up the areas of each of these rectangles, and that's going to give an approximation of the area. So adding this up, we would have the sum from I equals 1 to n of f of x sub I times delta x, where we think of the delta x in this case as being kind of the base length of one of the rectangles, and f of x sub I is what we use to calculate the height of one of these rectangles. And this summation here is very important, and the key thing to remember is we're adding up areas of rectangles, and the height of each rectangle is determined by the function value because it's enclosed between the function and the x-axis. Then what we said, just to kind of give a reminder, is that then the actual area would be the limit as n goes to infinity of this Riemann sum, because the larger n is, the better our approximation. And this limit of a Riemann sum is what we define to be an integral. So in this case, it would be from 0 to 2 of the function f of x dx. So let's take this basic approach and modify it to calculate an area between curves. To do so, we are just going to look at this motivating example. We're going to look at the area between the curve y equals x to the fourth, which is in red, and 2x minus x squared, which is in blue. So just from graphical inspection here, we see that the area enclosed is going to be between an x value of 0 and an x value of 1. So this point of intersection of the curve will be 1, 1, and the other point of intersection is 0, 0. So if we want to think about what the enclosed area would be here, we take the same approach that we did a few minutes ago. We take this interval from 0 to 1, we break it up into a bunch of subintervals, and on each of the subintervals, in a sense, we're approximating that enclosed area. So using the right-hand point to determine the height, we're going to go from the lower curve to the upper curve. And we do this for the entire interval. And then the idea is we add up the areas of those rectangles, and that's going to give us an approximation. So we would say the area enclosed here would be approximately the sum from I equals 1 to n. And then what we need to do is multiply the height of one of these rectangles by the length of its base. So the length of the base is going to be delta x, as it was before, this b minus a over n. But for the height, we see that we need to go from the upper function to the lower function. So the height in this case would be given by f of x minus g of x. So this is in general. It would be f of x minus g of x, where f of x is the larger function. So in our case, then that actual area would be the limit as n goes to infinity of this Riemann sum. So we see that the enclosed area here would be the definite integral from 0 to 1, so the interval that you're looking at. And what you integrate is the larger function, 2x minus x squared, and we subtract away from this the smaller function. And in general, this is an approach that you can always use for curves f and g. What you need to do is take the definite integral over the interval you're interested in. Here's 0 to 1. That's where the area is enclosed. The larger function, so bigger y value, subtract away the smaller function. So let's go ahead and evaluate. So using our work on the previous slide, we said the enclosed area is the definite integral from 0 to 1 of 2x minus x squared, quantity minus x to the fourth. So this would be the definite integral from 0 to 1 of 2x minus x squared minus x to the fourth. And to evaluate this integral, we're just going to use a fundamental theorem of calculus. We first go through term by term and write down antiderivatives. So x squared minus 1/3 x cubed minus 1/5 x to the fifth. And then by the fundamental theorem of calculus, we evaluate from 0 to 1, which means we plug in a 1, and then we put a minus sign, and we plug in 0. And when we plug in 0, we simply get back 0. 1 minus 1/3 minus 1/5 is the number 7/15. Now, when working through these problems, something very important to keep in mind is that we're calculating an area. And when you're calculating an area, the answer that you give should be non-negative. That is to say, if you ever get an answer which is negative for your area, that's going to indicate some mistake in your setup, whether your interval is incorrect or the ordering of your functions. Let's look at another example. Let's determine the area enclosed between the curves y equals x plus 1, y equals 9 minus x squared, and then the lines x equals minus 1 and x equals 2. So when attacking any of these area problems, the first thing that we're going to have to do is sketch the region. That's going to show us exactly what we are dealing with. So let's see here. We have the line y equals x plus 1. So that is going to be a line which has x-intercept minus 1 and y-intercept 1. So roughly speaking, looks something like this. And then we have the parabola y equals 9 minus x squared. So its vertex is going to be sitting on the y-axis at 9. The minus in front of the x squared tells us that it opens downward. So roughly speaking, maybe not drawn perfectly to scale, looks something like this, where this vertex is sitting at the point 0, 9. And we need to go from x equals minus 1. So see here, x equals minus 1 would be the line drawn here. And then x equals 2 would be the vertical line drawn here. And looking at our picture, we now see this nice enclosed area that we wish to calculate. And once again, as I've pointed out in previous videos, let me note again, the pictures that we draw for a situation like this is going to be purely to gain the intuition that we need. So your pictures do not have to be perfect, far from it, but what they have to do is hopefully, give you the intuition that you need to set this up. So the enclosed area is going to be the definite integral over how our x values vary. So we're going from x equals minus 1 over to x equals 2. And what we integrate is going to be the larger function, which in this case is this parabola 9 minus x squared. And we subtract away from the larger function the smaller function. The smaller function enclosing the area was the line y equals x plus 1. So now this is the new part of the problem, getting the definite integral set up. Hopefully the old familiar part is evaluating this. So just going through and kind of combining like terms, we have 9 minus 1 for an 8. We'll have a minus x, because remember this minus sign needs to be distributed into each term, and a minus x squared. So anti-differentiate each term. 8x minus 1/2 x squared minus 1/3 x cubed. And then we evaluate from minus 1 to 2. So we plug in a 2, so it'd be 16 minus 1/2 times 2 squared is 2, minus 2 cubed over 3, which is 8 over 3. And then we subtract away what we get when we plug in minus 1. So minus 8, minus 1/2, and then minus 1 cubed is negative 1, so this becomes a positive 1/3. And if we combine all of this together, it's the number 32 over 2. And once again, note, just from a very intuitive perspective, we're happy to see that the answer we're getting back is a positive quantity because it's representing an area of this enclosed region.